Good afternoon, everybody. Thank you for joining us for our webinar today for Technical Advances in Process GCMS. I want to thank you for taking some time out of your day or your evening, wherever you happen to be calling us from, to join us for this. My name is Teresa Russell. I am part of the Process GC team here at Wasson-ECE Instrumentation, and I'm also going to be your moderator for today. Before I introduce our speaker, who's John Wasson, I want to do a little bit of logistics for the call today. So everybody is in listen-only mode for this, and so I want to encourage you to submit questions as they occur to you during the seminar. We really welcome that, and the way you'll do that is on the side panel, you're going to see a tab that says questions, and if you just type your question in there, I'll be collecting them during the webinar, and we'll have a couple of points through during the webinar where John will answer your questions for you. So go ahead and let those fly when you have them. I wanted to start just a quick poll to find out how you heard about us today while I'm finishing my introduction. Let's see, additional points is that the webinar is going to be recorded, and we will send a link to you after the webinar is over and the video has been processed. It will automatically be sent to you. And in that email will also be included options for a certificate of attendance. I know some people had mentioned that they wanted to have a certificate of attendance, so there'll be instructions in that email for you on that, as well as how to join our email list if that's something that you decide that you'd like to do. And again, that'll come in an email after the presentation is over. So at this point, I would like to introduce our speaker for today, John Wasson. John is the founder and the president of Wasson-ECE Instrumentation, and I'm going to let him tell you a little bit more about the company. As to John's background, John has graduate work in chemistry, which makes him particularly well qualified for the discussion that we're going to have today on GCMS. He has a lot of background, not just by education, but by training. You know, for 37 years, he's been designing lab and process systems for our company, and in the process has learned a lot about what it takes to do GC right, and he's going to share some of that with you today. And you know, those systems that we've designed have gone to, I should say, all of the companies that you would expect, all of the big names in the hydrocarbon processing industry that you know, that we all know, Dow and Exxon and Chevron and all the other big names. So he's done a lot of really exciting projects, and he'll share a little bit of that with you today. So at this point, I would like to go ahead and turn it over to John.
Okay, thanks, Teresa. I think everybody can hear me now. Today we're going to talk about a new family of process analyzers. Specifically, this is our Eclipse line. We have a couple of different versions. There's one version that seems to be getting a great deal of attention. Excuse me, that's our system that does online GCMS spec. And some people are familiar with that in the laboratory. Now we're looking at putting it online, and a lot of people are interested in doing that. So that's what generates our talk today. So we're going to talk about the background of the company, what leads us down the path to online analytics, GCMS. We're going to talk about GCMS basics. So for those of you out there that haven't had really much of a foundation in GCMS, we're going to talk about some of those basic things. What are the strengths of GCMS? Look at some example spectra and kind of give you some background as to how this could be used online. The platform that this instrument goes into is the family of process GCs called Eclipse. We're going to look at Eclipse in detail and find out how these GCs are fundamentally different from typical online process gas chromatographs. At the end, we've got some examples, a monomer analyzer, which is mass spec, PDHID, FID. We're going to talk about a VUV fuels analyzer that's using an ultraviolet spectrometer. And the last example we have is a super RGA, which is 2 GCDs and an FID that does quantification from hydrogen all the way out to C20. So let's talk about Wasson-ECE, founded in 1986. We're one of 3 original HP channel partners Remember, before there was Agilent, there was HP 5890, 6890. And back in those days, they were looking for really a corporate partner to help provide turnkey solutions to their HPI base. So their HPI base knew they wanted a GC, didn't want to do the applications themselves. So HP was looking for a partner company, and that turned out to be us. So we would ask the customer, what samples, what do your samples look like? What analytes, what concentrations? And then we would build up a complete turnkey system, including columns, method, detectors, everything turnkey, ready to go. That was quite attractive to them. In that process, we realized that we wanted to be more than just systems integrators. If there was something that the problem required, a solution, a unique solution, we wanted the ability to invent that ourselves. So we accumulated chemical, electrical, mechanical, and software engineers. So if we saw something that was needed, we could invent it ourselves and not be limited to what else we could find in the market. After a certain period of time, we have 5,000 customized GC systems in the world in over 45 countries. We can take a moment here to dispel a popular myth, and that is that now Wasson is coming out with the Eclipse process GC line. They're just now getting into process GC. No, that's not correct at all. In fact, we've been producing the world's most capable process GCs for more than 25 years. People knew what we were capable of doing for the laboratory. They wanted the same thing online. So starting with 5890 and 6890, we just simply took those GCs, put them in large refrigerator-sized cabinets, purge, pressurize, heat, air condition them, and put them to work using capillary columns, temperature and pressure programming. And certainly they were unparalleled with respect to the chromatography and analytics that they could develop in the process environment. I'm coming to you from Colorado. That's our chief site for our main office technical and production work. We also have offices in Texas, Louisiana. Those are sales and support offices. Wholly owned subsidiary in Czech Republic. So they do lab systems and process systems for Europe and the Middle East. Another wholly owned subsidiary in Singapore. Their sales and support. A small company in Japan. Latin America, we have an office in Venezuela. In the past 37 years, we've accumulated quite a distributor network all over the world. So now let's talk about the basics of GC mass spec. Really, GC mass spec, which is different from straight MS. Straight MS has no GC in front of it. The entire sample is aspirated into the mass spec at one time. All the analytes are there. The mathematics, the deconvolution is very laborious and tricky, and unless you have a specific need for straight MS, that turns out to be more trouble than it's worth. What we're talking about is GCMS. So gas chromatograph in front to do the separation, then a mass spec detector. This is a simple diagram that we've snatched out of the library. It's showing a GC with a helium carrier gas. In this diagram, we have a syringe injection port. Obviously, in an online situation, we would be using either a gas or liquid inject valve in place of that syringe port. In the GC oven, we've got a capillary column. The end of the capillary column comes out of the oven, goes into the mass spec detector. So really the mass spec is just an add-on to the GC itself. The first stop inside the mass spec detector is the ionization source. So we use electron impact ionization. So you've got a hot filament, spits out electrons. The electrons fly across the vacuum, hit the analytes, the molecules as they come out of the column, and fragment them. And then we have electromagnetic lenses that collect those fragments and propel them towards the detector. The detector is an electron multiplier that sits at the back end of the detector. It's got a very high voltage applied to it. It's waiting for a little bit of kinetic energy to start an avalanche of electrons and enough current to feed a circuitry in our data system. So we generate the ions, we shoot them towards the detector. What we've got in the middle is called a mass analyzer or a quadrupole. So the quadrupole sits in there, and that has got a DC and an RF, two axes oriented at 90 degrees, and that field is manipulated at high speed with a computer dedicated to the mass spec. And basically, we can tell via that computer at any instant in time what fragment to look at, excuse me, what fragment to look at coming to let it pass through the quadrupole and hit the detector. For example, suppose I wanted to look at mass 31 fragment. I would set up the quadrupole via the computer to let only that mass fragment be able to traverse the quadrupole and hit the detector. Everybody else that's got a different mass is going to get deflected away from the detector and we won't see it. The next instant of time, I will tell the quadrupole to adjust to mass 32, collect the intensity of mass 32, then the next instance, we'll adjust the quadrupole to mass 33. And in that way, I can program the detector to look at different masses and collect the abundance of each mass. So you can see that circuitry going down to our data analysis. The top portion of that is a typical chromatogram like you would see on TCD or FID. But what makes this analyzer different is we're actually collecting an entire family of chromatograms. So think of the chromatograms as evolving in a third dimension. Each chromatogram is represented or a function of the mass fragment that we're looking at, for example, 31, 32, 33, 78, 76, whatever. And those spectra, the abundance of each of those masses is what's depicted in the bottom half of that graphic. So at each moment in time, I have the abundance of all of those ions. Similar compounds have distinct spectra. So now we just talked about how those molecules come out of the column and they get fragmented. It's kind of like taking plates and dropping them on the floor. Suppose when I drop a plate on the floor, it always fractures or fragments in the same pattern as a function of the plate. In the end, I could look at the fragments on the floor and tell you what the parent plate was. That's exactly how mass spec works. Each molecule fragments in a characteristic way, certain ions and certain ratios of abundances of those ions. So because they fragment the same each way, I can tell my data system to start looking for those fragments, looking for the abundances, and plot chromatograms, and I can identify the components in each peak. It's kind of like being able to look inside the peak and see what's inside there, what masses, what abundances are in there. And I can tell exactly what I'm looking at by looking essentially inside the peak. So in the end, I've got 3 layers of identification. I've got the GC chromatogram, which is basically the retention time of the peak. I can look inside that peak and I can look for the molecular or parent ion. That's the unfragmented ion. And then I can also look at all the daughter or qualifier ions. So these are other ions that are not only coincident with the parent ion, but they're there in the appropriate abundance ratios. I can apply all of these so that in fact, my molecules don't have to be actually have unique retention times. If I have some coelution, I can pull them apart as a function of that third dimension of chromatograms that I've accumulated. In a second, we'll see exactly how that works. So let's look at these 2 components. They're very similar, 2-chloropropane and 2-chloropropene. You can imagine if I had a boiling point column, those 2 components might elude the same retention time. For something like FID or TCD, that's going to be an issue. I would need complete separation. But now that I'm employing the mass spec, I can fragment those molecules and I can look at the resulting mass fragments or masses, or M over Z is mass divided by charge. And for chloropropane, I can see the major abundance is mass 43 and my parent is 78. But for 2-chloropropene, I can see something that is distinctly different. Now I've got my major abundance at 41 and my parent at 76. So what looks to be very similar compounds on paper actually fragment completely differently, and I can use that difference in fragmentation to build up unique chromatograms, do unique quantification. Here's 2 more components. These are hexane and benzene, both C6. Look at those different spectra. They are completely different. Hexane is major at 57 and parent at 86. Benzene doesn't even have a 57 and has a parent at 78. So I'm starting to appreciate how molecules that might look the same on paper are actually fragmenting quite differently. The power of mass spec is that I can use this detector to quantify just about everything except for hydrogen and helium. Those components are too light for the magnets that are inside the detector. Phosphine and arsine are very high priority catalyst poisons, so I can turn my mass spec onto those and I can look for arsine. It's major at 76, parent at 78. Phosphine, completely different. Here I've got a parent ion at 34. Speaking of catalyst poisons, oxygenates are right up that alley too. So let's look at two, methanol and acetone. Again, we just have examples here of two components that are different, not only in structure, but also in the different fragmentation pattern. And I'm going to capitalize on that to produce two separate chromatograms. Let's look exactly and see how that works. I've got methanol and diethyl sulfide. These are two of the components that I want to analyze in my sample. I have many other components, and I have this one particular column that I really like. The only problem is this column is going to co-elute methanol and diethyl sulfide. So what am I going to do to resolve that dilemma? Let's look at the methanol. Let's look at the spectrum of that one. Major at 31, parent at 32. Diethyl sulfide, though, is completely different. Major at 75 and a parent of 90. So in theory, I can go in and take different masses and I can plot different chromatograms and be able to solve that coelution problem. Let's just see how that works. Chromatogram on the left. I've got methanol and diethyl sulfide composite. In this particular column, they have the same retention time. What am I going to do? I'm going to go into my database after I've collected my run, and I'm going to say turn on extracted ion chromatogram for mass 31. And I'm going to see that chromatogram, which is the top one in the diagram. And down below for diethyl sulfide, I'm going to say give me an extracted ion chromatogram of mass 75. And now I can take each of those two chromatograms, I can integrate them separately, I can calibrate them separately, and I can generate two numbers that are unique, one for methanol and one for diethyl sulfide. But in fact, I was able to generate those unique chromatograms and solve the coelution dilemma. So not only with mass spec do I get real positive confirmation, I know what I'm looking at, but now I can even use that strength to pull coelutors apart. So unique strengths of online GCMS, confirmation. It's like we say, I'm essentially going to open up that peak and look inside. If things start shifting around, there's no guesswork, there's no ambiguity. I can look at the fragmentation pattern for each of those peaks and tell exactly which one's which. So I get confirmation. I look for the parent ion. I look for the daughter ions. They have to have the same retention time, and they have to have approximately the right abundance ratios. When those things all match up, I know exactly what peak I'm looking at. Mass spec is an excellent detector for sensitivity. It's got a broad dynamic range, 10 to the 6. I can easily go down to the single digit PPB. Flexibility, it's almost a universal detector. Like I mentioned, because of the magnet mismatch, it can't do hydrogen and helium, but really it can do just about everything else. And I like that because at 3 o'clock in the morning, when somebody calls and says, customers reporting that you've got something like acetaldehyde in our sample. Do we have any acetaldehyde? Have you ever checked for that? Now I have a way to react to that. I pull up acetaldehyde in my library. I look at some typical ions. I note the relative abundance of each of those typical daughter ions. I add those to my method, or I generate a new method. I run my chromatogram and I look and see if all of those ions are there at the same retention time at approximately the right ratio. If I do, then, oh my gosh, we do have some acetaldehyde. But if I don't, I can say no. To the part per billion limit, we don't have any acetaldehyde. Complete peak separation is not required for identification. We just looked at the methanol diethyl sulfide. You're essentially generating that third dimension of chromatogram. As long as I can get a unique chromatogram based on a unique ion, I don't care if they coelute or not. What is Eclipse and how is it different? So again, this is our own process GC. We wanted to engineer everything from the ground up. We did that with the exclusion of the mass spectrometer. That's Agilent's 5977 B mass spectrometer, the most powerful, most popular mass spec in the world. So we've been doing this process GC for 25 years, taking 58, 68, 78, 90 GCs and putting them in cabinets. So we know exactly what we wanted to do. We wanted to design something and build something that was targeted for the GC market and really be the same caliber or the same quality or the same capabilities as what you would find in the laboratory. You can do it in the lab, you should be able to do it online. What does that mean? It means you have to have temperature programming in microconvection ovens, true convection programming just like you'd find in the laboratory. Revolutionary temperature and pressure controls are required, and of course you want to use capillary columns. You have to have good temperature programming consistency if you're using capillary columns. As you know, capillary columns generate a lot of peaks, but if you don't have temperature pressure programming under control, those retention times are going to start shifting around and the whole thing's going to be wasted effort. So we want to do capillary chromatography just like the same caliber or quality that you do in the laboratory. We want to do that online. That was our objective. So the first thing we have to do is look at the ovens. And this company has a different philosophy, mechanical philosophy, when it talks about its ovens relative to other process GCs. We learned 25 years ago, if you want to have really a high resolution capillary chromatography, you need a convection oven such as you'd find in a laboratory. Most process GCs preheat their air and push it into a big box and kind of do their temperature programming sort of maybe that way. That's not what we wanted to do. So we changed our philosophy. We said, just like in the gray canvas, the Eclipse is going to be hazardous area rated class 1 div 2 on the outside when all the doors are closed and the system's purged and pressurized. When the door is open, in order to run the analyzer with power, you need to have a hot work permit. So it is not class 1 div 2 with the doors open. But as soon as you adopt that philosophy, that says, okay, I can do real programmable convection oven just like laboratory. I can do that online because I've changed my philosophy. It's still class 1 div 2 with the door on, but when you open the door, now you have completely different flexibility with respect to what kind of oven that you design. So our microconvection oven there is made out of a machined refractory. It's kind of something that would wrap around the column almost. It's like having an independent oven for each column in your GC application. More on the MCO in a second. In the middle, we've got subambient oven with Peltier. We've got isothermal ovens. We've got this little pancake that we're showing here in this picture. In the case of the mass spec, in the case of not mass spec, we have two conventional convection isothermal ovens. So plenty of oven capability so that we can do broad ranging applications with lots of columns. Okay, there's the microconvection oven, the picture in the lower right. You see the radial fan, the air doesn't go through it. It actually is slung outwards radially through the fence, heater fence through the column, and then it circulates up and then comes back down to the center of the fan. Let's look at the cutaway diagrams on the left side. On the top diagram, the doors are closed, so now it's in the temperature program mode. The air is recirculating inside the oven, through the fan, through the heater, through the column, up above, back down into the fan, temperature programming. When we finish our run, we want to cool back down. So if we look at the lower diagram, now the door is opened and the air is free to circulate outside of the oven. We even help push it out of the oven with compressed air that comes in from a proportional valve. That's that blue arrow at the lower right. So we open, push the hot air out, cool it down, close it like the top diagram, and start off on the next run. It's very thermally agile. Now that we've got those mechanics, what could we do with them? Let's look at that top table, retention time, reproducibility. Like we said a minute ago, if we can't produce retention times on a capillary column, we're just wasting our effort. So we did an experiment over 2 days. We took hydrocarbons from methane, pentane, all the way up to undecane, and we simply injected the same sample, same peaks, time and time and time again over 2 days. Then we calculated the relative standard deviation of the retention time repeatability. And you can look at that over 2 days. Those numbers are excellent. It's very repeatable. It's just like you'd find in a laboratory GC, like an Agilent 7890, 8890 running capillary columns. So we can do online what you can do in the in the laboratory. The second thing is we're using capillary columns, and so we have to have a split inlet. So a split inlet has to be able to inject or put on column the same amount each time. So we took methane, we injected it with our split inlet time and time again, and we calculated the area percent relative standard deviation. Again, excellent, 0.119. It's just like you'd find in a laboratory system. We have to do our own pressure controls. So we've got that too. It's method dependent. You load the method, it automatically programs the electronic pressure control, and you're off to the races. So we have forward pressure EPCs, we have back pressure EPCs. A back pressure EPC plus a mass flow controller equals a split inlet. So that's the data we just talked about. We have detector gases, we have gas saver mode, open up the split, make the injection, stop the split down, and conserve carrier gas. What types of things can we use? Mass spectrometer that we looked at, vacuum ultraviolet detector for doing fuels analysis like gasoline. PDHID is a pulse discharge helium ionization detector, and that's from Balco. FID and TCD we make ourselves. FID is single range 10 to the 7th sensitivity, just like you would find in linear dynamic range, like you'd find with Agilent. So we're using Balco components, Agilent mass specs, and ultraviolet detectors from Vacuum Analytics out of Texas. Safety features, we are designed for hazardous environments. In North America, that's NFPA Class 1, Div 2, groups B, C, and D. The T code or temperature code rating is T2B, 260 degrees C. Outside of the United States, we're ATEX Zone 2, X-proof, and the same T code rating, T2B. It is designed to withstand exposure to water, such as NEMA 3RX. It is a purge controller. It takes 20 CFM of plant air. That's what it uses to cool down its internals as those ovens open up and vent their heat. It does have programmable rapid purge on startup. So that means is if I do service and I close my door, some hydrocarbons may have leaked from the outside environment inside. I want to make sure that those are flushed out. So I turn on the system. It goes to the fast purge mode for X amount of time, and then it waits and then starts the power after the rapid purge has been completed. So any hydrocarbons that may have gotten inside the cabinet during my service work are ejected, then main power is started up. Remote injection means that our sample valves, gas sample valve, liquid sample valves, and those are placed in the sample system, which is located on the outside of the shelter. So most of our customers buy sample systems from us, but it's not required. But in any event, most people want to put their inject valves out there because they don't want to bring high pressure, high volume sample inside the shelter. So those sample streams just go to the sample valves inside the sample system on the outside of the shelter. We've got a list of features for ovens, 2 of which are programmable. They're lab quality forced convection. They're not preheat and then push it into a box. We like that. We can do packed and capillary, wide array of detectors, TCD, FID, PDHID, MSD, VUV. We can accommodate 4 detectors. Got a nice big 19-inch touchscreen so that it's easy for you to work on the method if you're standing in front of it. Otherwise, you can drive the whole system remotely. Gas saver mode, yes, we have that. Typical number of analytes. These analytes, a lot of detectors, a lot of columns, would typically measure a lot of different analytes, and we call that high data density. So one analyzer, multiple detectors, multiple columns, you're going to generate a lot of peaks and answer a lot of analytical questions each run. Let's look at some examples, and we'll toss out some chromatograms. So we want to look at our monomer analyzer. That's our principal target for the mass spec. And the fuels analyzers, VUVs, gasoline, and then the super RGA going up to C20. So neutrino is what we call our Eclipse with a mass spec detector on it. So let's look at that picture on the right. At the very bottom, you can see the Agilent 5977B mass spectrometer that's running a diff pump so that it has no problem with vibration, lasts a long time, does not blow up, excellent sensitivity. Right above the mass spec, I've got 2 programmable, independently programmable, microconvection ovens and 1 isothermal oven. So I've got a lot of capability with respect to places I can put columns in unique temperature environments. Right above the MCOs, we have another oven. that cover is removed so that you can see inside. On the left, you can see the PDHID. On the right side, you can see the FID. In between that, we've got some Valco valves, but those are not our sample inject valves. Our sample inject valves are out of the sample system. These valves are used for column selection, backflush, hard cutting, things of that nature. The sample comes from the sample system through the heated bridge. So if you look on the right side of the chassis, that black conical thing, the heated bridge goes right in there. That device gets shrunk down to make a tight seal. And that's how we have heated communication between our inject valves in the sample system and the rest of the analyzer located inside the shelter. Up above, we've got all of our electronics, pressure control, 19-inch touchscreen. On the left side of that upper cabinet, the silver-looking box is our Pepperell Fuchs purge pressure control system. The black box farther down is simply the main power disconnect. Lots of capabilities to do powerful chromatography. Let's look at the sample system. This one was built up for ethylene analyzer. And so this valves at the lower right, we could use Parker RMAX there, but not in this particular application because we're after trace components that would normally be found in the atmosphere. And so here we're going to use diaphragm valves. The diaphragm valves are all welded together, and we can do stream selection, calibration streams, QC check. All of these things can be accessed from outside the cabinet through our diaphragm valves. Right up above the diaphragm valves, hanging upside down like bats, we've got 4 gas sample injection valves. Those are Valco valves. And you can see on the other side of the oven wall, 4 actuators hanging upside down. Right above the actuators, we have a series of air switches because all of our valves are air driven. Just to the left of that, we've got class 1 Div 2 rated temperature controllers. Farther off on the left, we've got some black class 1 Div 2 rated power relays. And below that, the blue and white box is a rated power supply. We're going to use PDHID. In this application, that means no EPCs because they leak too much. PDHID is sensitive to everything except helium and neon, so an air leak would drive it nuts. So what we're going to do is use zero leak pressure regulators to drive just the PDHID portion of our analytics. So what you have there are 4 small zero leak pressure regulators, all welded up. They're going to supply the carrier gas to the PDHID. Inside the oven on the left-hand side, the black structure is simply a heater. If you look at that sample system inside the oven, there's a little white circle at the bottom. Actually, that's a perforation in the sheet metal, and you can see the insulation. When this system gets installed, the 16th-inch tubing that comes through the heated bridge will travel up through that hole and connect to the gas sample valves sitting up above. So that's how the sample makes its way over to the analyzers through that hole, through the heated bridge. Here's the plumbing diagram for both the sample system and the analyzer itself. Let's simplify things and just concentrate on the left side of the diagram. So here we have our diaphragm valves, and they're all ganged in series. So those are accessing through filters, different sample streams, calibration streams, QC checks, all things of this nature are going to come through those diaphragm valves. The last 2 diaphragm valves on the right-hand side direct the flow. We can either take the flow from our sample system and pass it out to sample vent number 1, or we can actuate those 2 valves and take the sample and pass it up through the gas sample valves. Here's the difference. When I want to flush out the tubing from my sample system by filters, etc., as quickly as possible, I don't want to push a lot of material through 16th-inch tubing. I want to use 8th-inch tubing. So in fact, the tubing that comes out of that last valve and goes down to sample vent number 1, that's 8th-inch tubing. That's for fast purge. And those 2 valves actuate, then the sample goes over through 16th-inch tubing and purges the 4 gas sample valves that you see on the right side of the diagram. 1, 2, 3, 4 are different gas sample valves. They can have different inject volumes, but basically the top 2 are connected to the PDHID subsystem of our analyzer. Valve number 3 is connected to the mass spec portion of our analyzer, and the last one, number 4, is connected to the FID portion of our analyzer. So now let's look at the analyzer itself. Those green lines up on top and the two valves, those are all associated with the PDH-ID. So the sample is injected, runs down the heated bridge, and then goes either to valve 1 or to valve 2 in the associated columns. And so what I'm going to do are my fixed gases on this PDH-ID, like hydrogen, helium, oxygen, nitrogen, CO, and CO2, especially for monomer impurities. CO is particularly tough. People like to see that down in the 10 part per billion range. Not a problem for PDH-ID. In the mid portion, the dark blue lines are connected to my mass spec. Actually, I have two columns in this train. One is column 5 and the other is column 6. Column 5 is a valve that's specifically targeted for light components. Column 6 is specifically targeted for mid-range components and heavier components. Each of those goes to the mass spec as a function of the method that's called out. So now I've got a column that does light and a column that does medium and heavies. I've got a very powerful combination so that if any other analyte were to pop up in need next month, next year, I've got an excellent column selection and mass spec detector. I can add those analytes on demand to my method. So my mass spec is going to handle methanol and other oxygenates, various mercaptans, H2S, COS, and arsine and phosphine. Down at the bottom, we've got classical FID in a two-column situation. FID is good for hydrocarbons. We're down in the 50 ppb range, C1 to C4 plus a C5 plus backflush. Let's look at some chromatograms. So this one is FID chromatogram. Peak number 4 is the ethylene matrix. Down below that, I'm looking at a C5 plus backflush. I've got my methane, ethane, my propane, propylene, acetylene, propadiene, isobutane, and N-butane. Excellent separation and excellent sensitivity. At the same time that chromatogram is evolving, the PDH-ID is generating this one chromatogram, really has two sections to it. When we switch sections and bring in different columns, that's what causes the baseline shift. Let's look at that chromatogram on the left side. Hydrogen, oxygen, argon, nitrogen, methane, and the all-important carbon monoxide. Then we switch in another column set. The baseline shifts up a little bit. Really, the only peak we're looking at in that second set is number 8, carbon dioxide. Okay, now let's look at our mass spec results. I've got methanol, I've got some mercaptans. Peak number 4 is carbonyl sulfide, 5 is H2S, 6 and 7 arsine phosphine. Look at those peaks. They are excellent, just like you'd find in a laboratory. Narrow, sharp, tall peaks. That means high resolution and also high sensitivity. So all three of those chromatograms are evolving at the same time. So that gives us fast throughput, maximum efficiency. So in summary, GCMS is designed to help you control your process. Number 1, we want no surprises. Anything happens, we don't want to be trying to figure stuff out. We want to know what's going on. Mass spec is the most powerful tool for doing that. Like I said, it's like being able to look inside each of those peaks and be able to know exactly what you're looking at. Increasing yields because we can find lots of things in a very short amount of time. That means increasing product quality. We can find off-spec feed faster, or also if we are feeding into a pipeline, then we can more dynamically qualify our product going into pipe. It's like generating a dynamic C of A because they're laboratory quality stuff. The entire world, in the case of monomer, it's about protecting catalysts. So Eclipse delivers lab quality data online. Faster results means you can react faster, nip any problems in the bud. Increased precision means increased on-spec product. There's less guessing, no ambiguity. Data density, again, is taking one analyzer and being able to produce a lot of data quickly. The alternative is to buy 4 or 5 of the other guys' analyzers and still not to be able to do all of the analytes that the industry requires. And the inverse of data density is to reduce cost per data point. We can do all these things with one analyzer. Cost per data point goes down. Okay, anybody have any questions on mass spec?
We've just had one question so far. Is it possible that we would have all types of detectors in one GC?
So right now, the most we've got packed into one would be the mass spec PDHID, FID. About October, we're going to come out with a 4 detector system so that we could put micro TCD in there also. But so far, that's the maximum that we've got addressed.
Okay, that's the that we have for everybody. Just a reminder, send me questions as they occur to you and I'll gather them, and then we'll have another pause here in a couple minutes and I'll put them to John.
Okay, now we're going to start talking about the VUV, but before we dive into that, this is a nice picture that shows the sample system. Right here, it's on a dolly, but it's going to be mounted on the outside of the shelter. And you can see that black tube, that's the heated line that's first going to push carrier gas out to the sample system, make the injection, and then sweep the aliquots into the analyzer. On the last webinar we gave, somebody had a question, would it be possible to build one of these on a dolly? Not only is it possible, we've done that, we've shipped them out. People are using them for kind of investigative work. They want to be able to move them around the plant. So we have a huge dolly, so to speak, that controls or mounts the mass spec. And then the sample system is mounted on the back side of that dolly. So in your mind, you can take that sample system on the right and just push him right around behind, and he's on the back side of the analyzer. And now with the dolly, you can push this around, hook it up to power, hook it up to sample lines, hook it up to communication line, because we're going to communicate to the DCS at the end of each run, and it's ready to go. So VUV is a vacuum ultraviolet detector. And basically, he's going to do a Piona type analysis on things like gasoline. So if you're familiar with AC Reformulizer or various companies that do DHA, it's going to be that type of quest. Take a very complex mixture and figure out different quantities of each of those principal components: paraffins, isoparaffins, olefins, naphthenes, and aromatics. We also want the ability to go in and pull out some individual components such as BTACs, benzene, toluene, ethylbenzene, xylene, and some oxygenates. So the detector we're using again is the VUV from Vacuum Ultraviolet out of Austin, Texas. Just as you may notice here, this system is a little bit temperature sensitive, no problem. We put a tiny class 1 Div 2 air conditioner on the side, and he's ready to go. So this is the output from the VUV. Looking at the gasoline sample, it's going to look through, it's using its retention time library. It's also using its spectrophotometer to go in and look at the structure of each of those components, match that to its library, and it's ciphering out which of the components are paraffins, doing that quantification, dropping them into the paraffin bucket. Isoparaffins the same way. Look at the entire chromatogram, figure which ones are isoparaffins, do the quantification, drop them into the isoparaffin bucket. Same thing for olefins, naphthas, and aromatics. What you have are reports that are basically those individual species as a function of carbon number, calculated in both mass percent and volume percent. Plus you have some unique components that are pulled out separately, such as some oxygenates and BTEX components. So we're looking at getting this data in about 33 minutes for gasoline. The third example is a super RGA. This is people over in Africa that are looking to generate alpha olefins. They needed to go from hydrogen all the way up to C20. So it's like a refinery gas, only it goes farther out. We're going to start at hydrogen, do the permanent gases, H2S above 200 part per million, and then we're going to look at C1 through C20, 2 TCDs, 2 FIDs, 2 microconvection ovens, 2 isothermal ovens, 8 columns, and the sample system to go with it. So what we have here is one single chromatogram that is the result of adding the outputs of 2 TCDs. One TCD has nitrogen carrier gas. His only job is to quantify helium if present and any hydrogen. Then that column set goes into backflush, and that's the end of his work. He doesn't produce any other peaks. So that lets us add in the TCD that has helium carrier gas, and it does the remaining components from carbon dioxide, ethylene, ethane, acetylene, hydrogen sulfide, oxygen, argon, nitrogen, methane, and carbon monoxide. In this case, we're not so much interested in the hydrocarbons because we're going to pick those off with an FID that we're going to see next. But as far as the hydrogen and all the fixed gases, that's what our two TCDs do. At the same time, that chromatogram is evolving. This FID chromatogram is also being produced. So here we're looking at the C8 plus backflush. Then we're going to start at methane, ethane, ethylene, all the way through to heptane, and peak number 23 is benzene. Excellent separation, very comprehensive quantification of light hydrocarbon components. But what about those heavy components? We want to go all the way out to C20. Let's look at this chromatogram. Notice all the peaks on the far left side. Those are not integrated at all. Why? We're not interested in that because those are the individual components that are separated on that last FID chromatogram. That column is excellent for light components, not good for heavy components. This column is running in parallel with the other FID and the TCDs, in fact. So we have three chromatograms being generated simultaneously. This guy wants to kick in about octane, then nonane, decane, endecane, all the way up to NC20, icosane at peak 13. Look at those peaks. Again, this is laboratory quality, capillary, high resolution, complex mixture. Narrow peaks, tall peaks, sharp peaks, just like you'd find in a laboratory. Now it's online. As far as Eclipse maintenance, being chromatographers, you know that 90% of your work is with valves and columns. So when that is required of Eclipse, that blue frame is latched in the vertical position. You can get at the columns and the valves from the front very easily when the door is removed. If by chance you have to get at the actuators or the air motors, you unlatch that blue frame, tilt it out. Now you can get at all the components in the back. For us, that was the best way to orient all the Valco valves in that top oven so they're pointing directly out at you. That's the easiest way for service, maintenance, leak checking, etc. Committed to service. I'd like to think that over the last 37 years, we are the best in the world with respect to servicing our fully applicated GCs. As you can imagine, that's a lot different from servicing just a vanilla GC that has no application attached to it. Really what we're doing is servicing the report that comes out of the computer to make sure that every one of the numbers is valid. So it's very challenging for us. We've been able to do it successfully for 37 years. And like I say, I think we're the #1 placeholder with respect to what the market's opinion is of us to support our lab machines. We're going to take that same reputation and roll it forward into online analytics also. Again, we're fully familiar with what it takes to make a GC produce the right results, not just deliver vanilla boxes. So we're going to do the online GC support just like we do our lab GC, and understand there's a different priority when it comes to online analytics. Lab systems go down for a little while. An online system goes down. It catches everybody's attention very quickly. So really, we need to be ultra responsive. A little preview of coming attractions. Not real jazz with sulfur chemiluminescence detector. So we have our own that's kicking around. We've tried it, seems to work. Sulfur specific detector, but it is completely linear and it's equimolar quantification, just like you would have on an STD. So you can calibrate with one of your favorite sulfur components, like carbonyl sulfide, and use that same response factor for all the other sulfurs in the sample. It's very sensitive and it's linear. Okay, other questions on the VUV or the Super RGA?
I do have a few questions for you. And while I ask these, I'm going to put up a poll for everybody. I'm just curious about really about what you analyze most regularly. I'm looking, it's kind of a popularity contest, I suppose. Okay, so the first question is how to calibrate the mass spec in an operational environment since you need several purge gases. I'm sorry, several pure gases. How to calibrate.
Okay, I'm sorry, I spaced that out. That was the first question?
How to calibrate the MS in an operational environment, since you need several pure gases.
So you don't need pure gases. You can use mixtures. It's exactly the same as calibrating a mass spec in a laboratory. If you're thinking about straight MS, that's a big issue. Straight MS, they have to use binary mixtures. So if I had 8 components that I wanted to analyze, I would need 8 different cylinders, each with only one analyte inside in helium matrix. So that's completely different. The GCMS systems are just like laboratory. You'd have compressed gas, you'd have LPG, you'd have ambient liquid, and those would be drawn in through the sample system, injected via the gas sample valves. You look at the data, you like it, and then you just push recalibrate on the data system. Okay, next question.
Then the next one is, does the system need to operate under vacuum?
So the mass spec itself operates under vacuum. There's a roughing pump that sits outside the cabinet, just like you would find a roughing pump in a laboratory. So otherwise, the main cabinetry, no, it's purged with plant air, but the mass spec is operating under vacuum. So again, the system is very analogous to what you would have in a laboratory.
And then concerning the sample stream selector, I wonder if all the samples are continuous flowing, since in the figure it seems that they don't.
Okay, that's a good question. The sample system, they are not continuously flowing. What you're talking about is the speed loop, and that's right outside the sample box. That is continuously flowing. So for example, you'd put a speed loop across a pump. The pressurized or discharge side of the pump would run up to where the analyzer is, where the sample system is. It would make a U-turn and then go back to probably the suction side of the same pump, and that pump then would recirculate fresh sample all the way up to the analyzer on a continuous basis. We would join that loop at a T, and we would draw in from the loop or loops into the sample system on a one-off basis. So speed loops right next to the analyzer, sample system itself, individual lines, one to each speed loop. Next question.
Do we need to define the sample gas composition and estimated concentration to the GC before start?
That's essentially the calibration process, and no, you don't need to do that at the start of each run. So you may want to recalibrate every couple of weeks. In the meantime, what you're doing is QC, injecting a QC sample. So a QC sample is a known run as an unknown. You look at the resulting concentrations. If those match what are known to be the concentrations of that blend, no need to recalibrate. If they start drifting away and the QC blend does not repeat the same answers, then you may have an issue. You need to go check that out, and you may possibly have to recalibrate the mass spec. But you don't need to do it every run. And the schedule, or you can put your QC blend in there once a day, whatever you want. And once a day it goes out, pulls in the QC blend, runs that, outputs the concentrations to the DCS, or has internal flags. And then if there's an issue, then it'll call your attention. You need to go check it.
And then do we have a comparison of our cycle time versus our competitors in the process GC category? Sure.
So we can do this. We can do any chromatography that our competitors can do. We can do in this system. There's nothing unique or magic or what they're doing. So we can do the same chromatography, which can be very limited and can be very fast. You know, we can do multiple segments at one time. Plus, we can do the more extensive list. For example, the entire battery for ethylene and propylene, we can do that in about 16 minutes. So that's pretty efficient compared to all the analytes we're looking at and the time constant of your process. So we have the ability to go both directions. We can go very simple, very fast, or we can add a few more peaks for a few more minutes and get a lot done, which is really still within the time constant of your plant or unit.
And then which item is our strong competitive point of our GC against our competitors?
The ability to accurately use capillary columns in a process environment. Capillary columns are very powerful. That's why you find them all over in the laboratory. That's where the best GC is done. So our number one strength is we want to have true convection, we want to have multiple ovens, and we want to use capillary columns to sort out quickly complex mixtures.
Are there any other questions? We have time for just a couple more. Here's another one, John. Do you have any limitation in any application?
Yes, we won't do online high temp sim dis, things that are going to cause you little tiny nightmares in the laboratory we don't want to have out online because it's seeing so many samples. You know, for example, in high temp sim dis, you have to clean up the column or cut off a piece of the column, service the inlet, etc. So, you know, things that can get reasonably through a lab GC, those are perfectly okay for us, but things that are a maintenance issue inside the lab are going to be even worse when you go online. So we don't want to do that. Right now, we don't have a super solution for sulfur, but that's going to be evolving shortly. We can do sulfurs in the mass spec, but as far as an equimolar sulfur detector, one that's going to be better than SCD, that's a couple months away.
I don't see other questions. We'll give another minute or two since we still have a couple. So while you're thinking, if you have any questions left, I just want to say again, thank you so much for spending part of your day or evening with us, depending on where you're joining us from. As I said, there'll be an email that comes out in an hour or two after this presentation that will have a link to the webinar in case you want to watch it again at some point. It'll also have a link for a certificate of attendance if that's something that you're interested in, and how to join our email list if you'd like to get tech tips or other information from us that we send out periodically. So with that,